Hi, and welcome to our spotlight presentation at the first workshop on radar perception for all-weather autonomy. In this talk, I'll be introducing the Oxford Radar RobotCar dataset. This dataset was released in September 2019, and at the time it was designed to be a new large-scale dataset to enable research in scene understanding for millimeter wave FMCW scanning radar for urban autonomous vehicles. This work was a collaboration between two groups at the ORI, the Applied Artificial Intelligence Group, or A2I, as well as the Mobile Robotics Group, or MRG. The release was spearheaded by Dr. Dan Barnes and was also in collaboration with systems engineer Paul Merkett, as well as professors Paul Newman and Ingmar Posner. The idea for the dataset release grew out of a partnership between our institute and our industry partner, Navtech Radar, to develop both the hardware and software required for all-weather sensing with radar as part of a UK research and innovation project. At the time of our release, compared to other heavily researched and exploited sensing like vision and LiDAR, scanning radar had not received as much attention in terms of robot navigation. We presented the dataset as an extension to the Oxford RobotCar dataset. We completed 32 traversals of a central Oxford route during January 2019. This brought us to a total of 280 kilometers of driving and almost 5 terabytes of raw sensor data. Contributing to this total were sensors identical to the original RobotCar dataset, including a stereo camera, 3 fisheye monocular cameras, 2 push-broom 2D LiDARs, as well as a global positioning and inertial system. However, contrasting to the original RobotCar dataset, our vehicle was equipped with a Navtech CTS350X, scanning radar, and 2 Velodyne HDL32E 3D LiDARs, as well as ground truth radar odometry. FMCW radar operates by taking measurements of the environment as an antenna spins around its complete 360-degree field of view. The resulting scan is suitable for localization and scene understanding, and it is unencumbered by environmental conditions such as fog, rain, snow, lens flare, or even complete lack of illumination. Additionally, in some configurations, radar can take measurements at hundreds of meters of range, which will prove to be a particularly useful characteristic for the decision-making ability of vehicles traveling at speed in motorway situations. At the ORI and with our industrial partners, we are really interested in deploying this sensor on mobile robots across a range of platforms and application domains. The platform used was a modified autonomous-capable Nissan Leaf, as per the original RobotCar dataset. In 2012, this very same vehicle was used to demonstrate autonomy on UK roads for the first time. The route driven was around central Oxford, which presents itself as a mix of dense urban and suburban scenery. We visited iconic landmarks such as the Sheldonian Theatre, as well as busy commercial spots such as shopping centres and Oxford Central train station. The basic measurement process for radar presents dense polar grids. In the configuration used, there are 400 azimuths per sweep, or rows, and 3,768 range bins, or columns. We do not provide Cartesian scans for download, but we do provide scripts for converting to this format at variable maximum ranges and Cartesian resolutions. The specific radar configuration used provides 4.38 centimeters in range resolution and 0.9 degrees in rotation resolution, with a range of up to 163 meters. In other configurations, our radar can provide in excess of 650 meters in range and higher rotation speeds. However, for dense urban environments, the increased resolution was thought to be more desirable. We provide Velodyne data in 2 formats, a raw form, which encapsulates all the raw data we recorded from the sensor for users to do with as they please, or in binary form representing the point cloud for a particular scan. Precise extrinsic calibrations for each sensor are included in the development tools in order to allow for cross-modal data association. To demonstrate the robustness of scanning radar in demanding urban environments, our dataset encompasses a variety of weather, traffic, and lighting conditions. We released optimized ground truth radar odometry in order to encourage research in this modality around motion estimation and localization. The provided relative poses were obtained using visual odometry, visual loop closures, and GPS across all overlapping traversals of the same route. The data has been available for download online for the last 18 months, and we are very happy at this stage to have more than 400 registered users at last count. To gain access to the data, we require registration with an email address associated with the university. We also provide tools for working with the data integrated into the SDK for the original RobotCar dataset. We also provide tools for easily downloading the entirety of the dataset. If you do use this dataset in your research, we ask that you please cite both of the following papers. In comparison to alternative datasets that have emerged alongside and after our release, we feel that ours serves a particular need for localization research, in that it revisits the same route many times. We are, however, impressed by the two major alternatives. Firstly, Keist-Smulran is collected over diverse scenery in different parts of a city, which we think will be important for learning models which generalize well to different radar scenes. Secondly, Heriot-Watt's Radiate includes ground truth positions for traffic participants, and it also collects data in heavy snow. We are super encouraged to see the impact being made by our dataset. Work in this area has included all autonomy enabling tasks from a number of research groups. And so I'll mention a few in the last part of my talk, but this list is by no means exhaustive. Our dataset has featured heavily in research on motion estimation. This research has seemingly covered the application of traditional computer vision techniques, the advancement of radar-specific signal processing, and various end-to-end systems which benefit from the large quantity of labeled consecutive frames in our release. The dataset has also spurred research in place recognition, which has included a focus on rotationally invariant metric learning and sequential filtering. We have even seen joint radar-LiDAR place recognition, combining the advantages of both modalities. More recently, at this workshop, we ourselves release early results outperforming previous works by unsupervised learning. We have generally found that the quality of raw GPS INS that we have released is sufficient for learning and testing of this place recognition task. The ground truth relative poses we have released have also successfully been aligned against each other to enable research into metric localization. Contributions in this area have again covered end-to-end probabilistic, hierarchical, and cross-modal approaches. Although, as I have mentioned, our dataset does not include ground truth object positions, it has been used in weakly supervised systems to develop a segmentation capability in radar. This has been particularly benefited by the surround view cameras and high-quality 3D LiDAR data, which are synchronized with and released alongside our radar data. Our ground truth radar odometry has also been used as a source of human demonstration for a system which learns which parts of the scanned scene are drivable, towards understanding how to drive using radar data alone. Finally, and very recently, our dataset has been used to learn a model for realistic and stochastic simulation of radar measurements from data collected elsewhere, as well as from synthetic scenes taken from typical autonomous driving simulators. This is, of course, an ongoing area of interest for researchers at our institute. We are, of course, still deeply intrigued by what this sensor can help us achieve for mobile autonomy, in terms of helping intelligent machines to understand how they are moving and where they are, what surrounds them, and what they should do next. We are also interested in what this sensor can help us achieve outside of urban environments. And I'd like to point you to our upcoming dataset release across a wide variety of UK driving scenes, including driving in difficult off-road conditions and wild scenery from the Scottish Highlands, where radar is a core focus in this collection. I would like to, on behalf of my co-authors, thank you for watching our presentation and your interest in our dataset. I'd also like to thank the workshop organizers. It is so exciting to see the increasing interest in this technology at sessions like these. If you have any questions, please do not hesitate to reach out to me personally or to the dataset management team generally. Have a great ICRA 2021.